Let's look at one final example of a functional relationship, but one that uses not a continuous or quantitative predictor, but rather groups and how that relates to the outcome measure. Let's pick an example that's a little closer to home. In this case, parking permit costs at UCSD. Suppose we go into a parking lot and actually ask 100 randomly selected individuals how much they're spending on their annual permit. Notice we again have variability in the response. That is, people are differing in the dollar amount that they say they are spending. Now, you might have guessed that we can represent these differences, that is, we can functionally relate them to something on the basis of the type of permit they're actually purchasing. Again, each of these dots is actually all the people we measured. So all the people who purchased an A permit are up there at a little over 1,100, and all the people who purchased an M permit are down there a little below 300. Now again, we can relate this in terms of a mathematical model. We can do it in this way. Price of permit is equal to some baseline, some zero, plus the actual cost of each permit. And notice that that does describe perfectly the functional relationship between the type of permit someone purchases and the actual dollar amount they're spending. Now I want to show you another way we can represent this mathematical model, and one that will be more convenient for us as we go forward and try to make inferences about populations. Remember, the whole purpose of our mathematical models will be in the service of making an inference about a population, and so we want our models to most facilitate this type of inference. But the model I'm going to show you will represent the exact same thing as this model, except we're going to do it in a different way. Let me show you what I mean. Instead of representing the different groups there as the dollar amounts of each permit, what if we represent them as a difference from an average cost? So here's what that would look like. The price of the permit is equal to some overall average, the average amount that permits actually cost for those different categories, plus some cost offset, some difference from that overall average. Let's see how this looks on the plot I showed you before. So here again we have the cost on the y-axis and the different permit groups. Let me draw in that overall average. That's the overall average of all the different permit costs. Notice we can draw in the offsets graphically. The A group is above average by that much. The B group is also above average. The M group pretty far below average. And the S group only a little bit below average. Now pay attention to the y-axis, because instead of representing cost, let's represent this as cost offset. That is, the degree to which these groups are differing from that overall average. And so notice that's what our function here, or our mathematical model, is really representing. Our overall average plus some cost offsets. Now this type of model is known as an effects-coded model, and it's going to be more convenient for us as we start to make inferences about populations. But I want you to notice that it really is representing the same thing as simply those group means. What is the average cost of an A, B, M, and S permit? Except now we're representing those groups' locations in terms of two things, an overall average plus a deviation from that overall average.